Okay, thank you. Okay. No, it's working. So I would like to thank the organizer for giving me the opportunity to present some of our work on free space optical communication, and also to give me again the opportunity to meet with faculty colleagues at Sup'Com and as well as PhD students. So I would like to start with a disclaimer by saying that I am not really an expert in optical wireless communication. Actually, I started working in this area about a year and a half ago through some PhD thesis. But what I would like to share with you is what I learned over the last year and a half. And the way I will structure this kind of extended talk is probably about 2 hours talk. Like the first hour will be a heavy tutorial on one aspect of wireless optical communication, which is free space optical communication. So I just would like to get an idea of the knowledge, or the general knowledge of the audience. How many of you heard of this word free space optical communication? Few. Okay, so you know about this technology, some of you. Maybe others don't know about it. So that will be an opportunity for you to maybe, at least at a high level, learn about this technology. So that's the first part will be tutorial. What is free space optical? What is it used for? What are the main challenges? What are some of the solutions that have been proposed over the last years? And then the second half, after the break, I will maybe highlight some of our research work in my own group, kind of some of the maybe problems that are in a way linked to free space optical communication. And as you will see, they are along the lines of things we do in our group, which is on the performance analysis area. So the talk actually is going to start with some of the motivation behind free space optical, which is spectrum scarcity. Spectrum scarcity is one of the main issues that we see these days, and based on the presentations I looked at in the program and the presentation given this morning by Mohamed, obviously spectrum is an issue, and one of the solutions is cognitive radio, which we are not going to address here, but they are all going into the same direction of trying to address the spectrum scarcity problem. So I will talk briefly about the spectrum scarcity problem, and essentially I will introduce the potential solutions before getting into free space optical communication as one of the main solutions that many people are advocating for some niche application. It's not a solution for all kind of problems, but it can be a solution for some kind of applications. And then we'll move into the potential and application of free space optical communications, the challenges that this technology is facing, and the solution that people are proposing to address these challenges. And then, as I told you, in the second half of the talk, I will be talking about some of the recent results from my own research group on some of these problems related to free space optical communication. I will conclude with some basically summarizing and concluding remarks. So when we talk about the spectrum, we are usually referring to the radio spectrum, which go from 3 kilohertz to 300 gigahertz. It's a national resource. It's it's scarce, and it's usually basically exclusively monitored and regulated by the state. In every country, the state regulates the spectrum, allocate licenses, optimize the use of the spectrum to get revenues and to basically provide the public service. So it has multiple basically purposes, and as such the RF spectrum is allocated to multiple applications, starting by radio and TV broadcasting. Different kind of government and public and industrial application needs the spectrum, such as military, police, public safety, and so on and so forth. All of them need their part of the spectrum. And then over the last 20 years or so, this exponential growth of mobile and wireless application for basically regular users for both voice and data is consuming more and more of this spectrum. Now, this is a classical chart that you will see in all kind of conferences, just showing you with the multitude of colors that is available in this chart that most of the spectrum has been allocated in the US at least, and basically we are getting into a spectrum congestion kind of situation. So this is actually, as a follow-up, a study that has been done by FCC in the US, and what the study shows, it shows in one hand the kind of growth of the traffic over the years. This study was done in 2013. or I think 2012 rather, and then this is so based on historical data, and these are prediction at that time, and it shows the kind of exponential growth of traffic of wireless applications. And then, corresponding to that, we see how the spectrum is being used. So we have here a surplus of spectrum, and then the prediction of FCC is by 2013, we are getting into a spectrum deficit. Okay, so if we continue using the way the spectrum is being used now in the US, the prediction is that basically we are running out of spectrum. Now, there was some criticism for this kind of study, so I'm not sure how accurate are these numbers, but the point is not like to look at absolute numbers. The point is to mention that this is definitely a serious issue. Spectrum management and spectrum scarcity due to the exponential growth of smartphone and all kind of smart devices with wireless application is basically a reality. So for instance, you can see here between 2011 and 2016, global wireless data traffic is expected to increase 18 times folds. So all this led to the so-called spectrum crunch or spectrum exhaustion problem, and this led to many people, I mean, and that's not new, but basically more and more people are looking at different solutions to address the spectrum crunch problem. So the way you can categorize these solutions, or at least one way to categorize the solution, is to put them in these three categories. So the first category is basically trying to be more spectrally efficient with the current kind of system, or by adapting the current systems. And this has been done over the last 15 years or so by talking about people talking about MIMO systems with data, multi-streams of data on multiple antennas, adapt modulation and coding, where basically you are adapting with respect to channel variation. These kind of techniques are there to try to increase or try to get close to the channel capacity. Or in other words, what we are trying to do, you are trying to improve your bit per second per hertz. Okay? These are the kind of objective of this first category of techniques. And pretty much we are coming also close to saturation here. People have basically used all kind of tricks and techniques to come very close to channel capacity, even over fading channels. The second category of problems is essentially trying to be more aggressive, temporarily and spatially, by reusing the spectrum. That's also a trick that has been used since day one when cellular technology has been developed. It capitalized on the fact that we are going to reuse the spectrum. Now there are different variations of this kind of idea through cognitive radio, where we are allowed to transmit, with as long as you don't interfere, or you don't interfere beyond a certain level, or this notion of offloading, where you're going to put a high density of small cells that are going to capture basically the traffic generated by hotspots. It's an old idea that is pushed to its extreme, and basically it goes along the line of the solution that are trying to use more aggressively the spectrum, spatially or temporally, and in a way you can think of these solutions as trying to improve the bit per second per hertz per meter square. We are trying to increase the area spectral efficiency of the system. So that's solution one, or category one. That's category two. But then, if you run out of all of these kind of solutions, what can you do? Obviously, there is an obvious solution to try and get to the unused part of the spectrum, or to the part of spectrum that traditionally has not been used that much for wireless applications. And by that, people are talking about developing system in the 60 gigahertz up to 90 gigahertz or millimeter wave, and that's a very kind of popular area these days. Now, those of you who went to the recent ICC or Sup'Com, a lot of work is being done these days in millimeter wave communication. Now, there is also kind of interest by some IEEE kind of it's not at the standard level, it's like a special interest group or within IEEE trying to push for terahertz communication. So terahertz is that part of the spectrum between RF and optical. And it is used for imaging, or there are a potential of using terahertz for imaging purposes, but there is also some research who are advocating that terahertz band can be quite useful for communication application. And then finally, there is, if you go beyond RF, beyond terahertz, you are going to reach the optical spectrum. And there is a large set of researchers that believe strongly that we should capitalize on the optical spectrum to communicate. Obviously, this comes with its own challenges, and as such, basically there are different solutions that have to be developed to be able to use the optical spectrum. So why there is a need for optical wireless communication? I would say the main kind of argument behind this is that there is a huge unregulated and licensed band beyond the 540 terahertz that kind of delimitate the optical region that can be used to deliver high data rates, and that can be a solution to the so-called last mile problem, which I will be talking about down the road in some of the slides. And when we talk about optical wireless communication, I would like, as I told you in the beginning when I mentioned the disclaimer, it's a very broad area. There are full books now just on optical wireless communication. What I will be talking about today is just one aspect of optical wireless. So what I would like to mention in this kind of first slide on optical wireless communication, the variant of optical wireless communication, because there are different variations. First of all, usually there is the so-called indoor and outdoor kind of optical wireless. Indoor, there is the infrared. We like the kind of remote control. It has been there for a long time. It's like basically low data rate, usually kind of communication that used for remote control applications. That has been, as I said, basically used for a long time. But more recently, within optical wireless communication, there has been a great interest in the so-called visible light communication. So visible light communication, as the name indicates it, is very simple, is to use the light, what we have here, for communication purposes. Now, I'm not going to be talking a lot about this today, but it's also a booming area. A lot of people are interested in visible light. Japanese, Korean picked up very early in that since 2003, 2004. They formed a consortium. There are some products available, and I assume that this technology can basically pick up at any point. And what they are saying, or the argument they are using, is light, especially now with LED that are extremely efficient, can be used to communicate if you modulate light. Because basically, if light is modulated at a high speed, you will not notice it from a lighting perspective because it will be basically beyond the sensitivity of your eye. But you'll be able to use this modulated or intensity of the light to basically send information from the light that is being used anyway for lighting. That's kind of the idea behind visible light communication. The principle is very simple, and there are a lot of demonstration of this technology that has been shown, as I said, mainly in Japan and Korea. And most of the work that has been done in VLC is in the area of equalization, because there is a lot of work to be done in equalization within VLC, and MIMO. We have done some papers on MIMO for VLC when you would like basically to have an array of basically LEDs to communicate with the user. And I can give you some references on this topic, but this is not a topic I will be talking about much today. Now, the topic of choice today is what people call free space optical communication, which is essentially for outdoor application and mainly for point-to-point, but as you will see, it can be used also in network layout. And this is basically using lasers and photodetectors to communicate extremely high data rates over the air, or trying to achieve fiber optic kind of performance, but over the air. So let's try now to see the basic principle of FSO, and FSO stands here for free space optical communication, and based on that we'll try to explore some of the challenges and solutions. So the basic principle is as illustrated in this kind of figure. What you have here is basically a laser, or actually two lasers in this particular case, on the top of a building, and each one has also a photodetector. So what FSO here is being used for is to connect using narrow beam two optical wireless transceivers, which is a laser and a photodetector, in line of sight. Okay? Now, for the source or the optical source, you can use a laser or an LED. Most people use now for free space optical laser because lasers tend to be more power efficient and basically can deliver higher data rate. And this optical beam is basically propagating over the air or over the atmosphere, and it's received by a lens and then by a photodetector. You can have a full duplex kind of transmission because you can use two wavelengths. You have plenty of bandwidth available. You can use one wavelength for one direction or one uplink, if you will, and the other wavelength for a downlink. We'll talk more about this later on, but there are three optical windows that have been identified, but I will tell you later on why this is kind of the bandwidth window, or the window that is basically gaining momentum. And now, just before getting into details, I would like to give you some numbers to show you the potential of this technology, and I forgot to put here some references. This technology, like in the fiber optic domain, can be used in a WDM format. And WDM stands for here, wavelength division multiplexing, which means you can multiplex on multiple wavelengths, basically different data streams. So a lot of the work that has been done in this area are by people coming more from the physics and I would say optics background, not really from a communication technology background. So these are people who have a lot of experimental skills, a lot of optics engineering background. And for instance here, we have a team in Japan which demonstrated a couple of years ago 10 gigabit per second over 1 kilometer. And the way they achieve the 10 gigabit per second is by multiplexing basically over 4 carriers, 2.5 gigabits kind of data links. Now, more recently, I think less than a year ago, I would say even a couple of months ago, or 6 months ago, there is a group of Italians who were able to demonstrate 1.28 terabit per second. So really, we are talking about a huge amount of data, over 210 meters. And this was achieved by multiplexing basically over 32 carriers, and each carrier was carrying 40 gigabit per second. So the potential is huge. The data that can be carried over these links is really tremendous, and that, as such, people are starting paying attention to this technology. Now, let's talk now a little bit of the details and give more information about how free space optical communication works. So, as I mentioned earlier, the debate here, when you use an optical source, are we to use the LED, which is often used also for lighting purposes, or a laser diode? The usual kind of discussion that happens, or the trade-offs, are in terms of output power. Usually laser diode will achieve or will give you a higher output power. The spectral width, laser diode also will give you narrower, cleaner, I would say, spectrum width, spectrum lines. The electric optical efficiency, like how much efficiency you have in the conversion between the electric data stream that is coming from this point and that's being converted to an optical wave. The efficiency, again, laser diode will win. They tend to be more efficient. The safety, and when we talk about safety here, we talk about eye safety. It can be, of course, very dangerous to put yourself in front of a laser. Like lasers are classified in different classes, class 1, class 2, class 3. There are some class of lasers that are very, there is no problem with them. But there are some, like when you go into the high class of laser with high power, you know, obviously it's very dangerous to be in front of these lasers. Whereas for LED, they are the purpose of LED for lighting. There is no safety issue whatsoever. So safety is another aspect that one has to look at when he wants or she wants to design an optical wireless communication system. Directionality, LED tend to be more omnidirectional, whereas laser can be more directional. Reliability, again here LED will be winner in terms of how often you need to maintain and to basically change maybe the laser or the LED. And the cost, the LED tend to be cheaper than the laser. So, all in all, LED has been used mostly for VLC, visible light communication, for indoor application. For outdoor application, if you are targeting, you know, basically a certain considerable range, mainly you'll be going for a laser kind of source. In terms of receiver, essentially there are two kinds of receivers. There is a cheap PIN kind of diodes, or the avalanche diode that are mostly used now with different kind of materials depending on the window that you are operating over. Avalanche tend to be more, I would say, they are a little bit more expensive, but they have a higher sensitivity and better performance than the PIN kind of diodes. Now, in terms of the medium of transmission, so you are transmitting over the atmosphere. And this is like a channel response. You see here the attenuation as function of the wavelength. And we notice here there are three windows of transmission. This one around 8.50 nanometer, another one around 1.3, 1300 nanometer, sorry, and another one around 1550 nanometer here. Okay? Now the nice thing about these three windows that they match the windows that have been used for fiber optic communication traditionally. which means the equipment, transceivers, lasers, and photodetectors that have been used for wireline fiber optics can be reused in an efficient way for free space optical communication. Now, the only difference is that there is this kind of AI safety issue that come into play. So basically, below 1400 nanometer, the eye is very sensitive to light. Essentially, it will go all the way, it can affect the retina. Above 1400 nanometer, it is well known, at least people who are expert in this, will tell you that the eye is less sensitive to light. In other words, the cornea can act as an absorber of light. So you can use lasers with higher power if you are using basically a wavelength of light above 1400 nanometer, which makes this window of particular interest for free space optical communication to basically go around the problem of eye safety. Now, let's try to see why FSO is becoming popular. And, and as you will see, this is not a new technology. And I will show you later on a small kind of maybe movie explaining or mentioning briefly this. It has been there for some time, but it's becoming kind of an interesting over the last years for a few reasons that are listed here. So first of all, it's license free, at least so far. So far, the government is not going to come and ask you for traffic utilization or tax or license fee for transmitting in the optical spectrum. That's obviously not the case. If you want to submit or to transmit in the RF spectrum, you will have to have a license. It is cost effective. It's cost effective because in many instances you are essentially going into what people would call a brownfield. You have an area where basically things are already established and you don't have high connectivity or you don't have high fiber optic availability. So instead of going and digging and trying to put fiber optics, you can on the air basically form your free space optical network and afford in a way at a much cheaper cost, fiber optic kind of communication, but on the air, rather than going and digging and putting basically all the infrastructure after basically building, having buildings in place. And that's why it's called suitable for brownfield. And it's cost effective, doesn't cost much. You don't have fiber optics to lay out. You just need a laser and a photodetector. It can be used behind windows. You don't have to go and get access to roof and get, roof rights can be sometimes quite expensive. You can place your laser behind a window. You may have to live with a certain extra attenuation, but essentially in any floor in a building, you can have your laser pointing to another photodetector that can also be behind a window without having access to a roof. Fast turnaround time, which means you don't have to basically set up your network and live with it forever. You can put it for a temporary event, and we'll talk, that's one of the main applications of free space optical communication, to deal with a temporarily high intensity or high traffic demand event, and then disassemble your infrastructure, and basically it can be very fast in terms of putting together the network and dismantling it. I mentioned already the fact that it can be suitable for brownfield. Very high bandwidth. A lot of bandwidth is available in the optical range of the spectrum. Very similar to fiber optic kind of basically performance. So that's of course one of the main advantages, availability of high bandwidth that is unregulated. It's health friendly, and many actually, in general, optical wireless is friendly. Beside the eye aspect, there is no RF hazards. So for instance, in many hospitals, people are exploring visible light communication as an alternative for communication because they do not want to have any electromagnetic radiation or basically interference with their kind of equipment. So if you use optical spectrum, either through a laser or through visible light communication, that's usually a very welcome solution. And one key aspect, especially if you use narrow, high-efficiency laser beams, is basically quite energy efficient. The energy is focused on this laser beam. Is immune to interference. You don't create interference because it's not like RF where you're broadcasting information and you are creating interference right and left. And also, and that's why it has been used essentially in its early age by military people, it is very secure in the sense that you cannot intercept a free space optical link unless you are really within the path of propagation of that link. Now, what are the possible applications of free space? So as I told you, it's not a new technology. as soon as the laser was invented in the 60s, people start talking about free space optical communication. But the first people who picked up the technology and actually built systems are the military, and there are a lot of confidential or classified work that has been done by military in terms of secure free space optical communication, and also for space applications. Because in space, one of the main issue behind, one of the main challenge behind free space optical communication, which is the atmosphere, is not there. So basically, satellite-to-satellite communication can be done over thousands of kilometers using a laser light without basically being affected by atmosphere. So it has been used for inter-satellite communication for a long time already. But now people are trying to start using FSO over the last, I would say, 5, even 10 years, people start talking about FSO, but now it's picking up more and more over the last years, is basically for commercial applications. So what are the possible applications one can think of? The so-called last mile solution. So you have one building in the whole area that is connected to the internet backbone. All other buildings are not connected via fiber optics, but they would like to benefit with high connection that this building is benefiting from. Instead of trying to lay down fiber optics to connect all these buildings, you just need to set up a laser and a photodetector on the top of these buildings, and essentially you are offering the last mile solution or the last mile kind of high data rate connectivity to these buildings. It can be used as an optical fiber optic backup. So basically, you may have a fiber optic available, but it can go down. There can be facing some network problems. So free space optical can be completely independent network that can give you service in case your fiber optic underground kind of system basically goes and is an outage. It can be an excellent application or can be an excellent solution for high data rate, temporary link, or disaster recovery. So you have a certain conference or an Olympic Games or a World Cup. So essentially you have an event that will, or Hajj, for example, that is requiring tremendous capacity over a short period of time. But basically, you don't need that capacity forever. And as such, one possible solution is to set up your free space optical network, use the capacities offered by the network over that short period of time, dismantle the network, and basically, you don't have to build a permanent network to achieve that capacity. Same thing if you are dealing with a disaster operation where your network is completely shut down, you can build quickly a high, basically, high data rate network using FSO technology. It is also useful for what we call difficult terrain. Difficult terrain, you have a river in the way, and you need to have connectivity between the two borders of the river. It's difficult maybe to dig under the river, or you have a terrain where you cannot have a fee. It's not possible to dig because the person who owns that particular terrain doesn't want to give you rights to go over his field. You can put basically a free space optical link to bridge basically two areas across a river, for instance. That has many applications actually when you go, and I will tell you a little bit more about these companies. Many of these applications go around this difficult terrain problem. Now also, recently people have been talking about the cellular communication backhaul. Now, with all these femtocell emerging solutions, people have to connect all these femtocells to the macro cells, to the mobile station, and so on. And this is not being done anymore, or is not being proposed to be done anymore via the wireline network. People are proposing actually a wireless solution for the wireless backhaul. And actually, one of the main solutions that's being kind of proposed is a so-called 60 millimeter or millimeter wave kind of technology as being the solution for the wireless backhaul. Actually, free space optical can give you even better performance than 60 millimeter wave. And it can be a very good application, it can be a very good solution for the wireless backhaul. Actually, with 60 millimeter, and I will talk about that later on, they can complement each other perfectly, and they can give together probably the best solution for the wireless backhaul. High definition TV and camera, this is also being used these days in some of the companies. I was surfing the web that are selling this kind of product. If you have like a, like this company that, this like TV station that would like to transmit information from a remote location, and it's a high definition TV, free space optical transceiver can be a very good solution to deal with the high data rate that this kind of high definition TV can generate. So, Before getting into some examples of deployment, I would like to say that obviously, free space optical communication, because of the nature of the point of the, or the laser beam kind of communication that is involved, is essentially point-to-point. But this does not mean that it is only for point-to-point communication. There has been multiple solutions or multiple examples of deployment of this technology for example, point-to-multipoint. So you have a point here that is, let's say, generating information, and this can go to multiple points, which means you have a point-to-point here, a point-to-point there, and a point-to-point here. It can be a mesh architecture. And people use or are talking about route diversity often when they talk about FSO. When you set up a network on the air, so you have all these buildings connected, and maybe this is connected to this one and so on. You can have multiple routes to reach one particular destination, and maybe depending on atmospheric conditions or depending on scintillation conditions, which we'll be talking about later on, you can pick one route versus another route. So what I'm trying to say, these kind of FSO links can be used in a point-to-point fashion, but also there are solutions that can come as a network solution to connect a full campus or to connect a full, basically, industrial kind of campus or industrial, I would say, company that would like to connect different units in a free space optical fashion. Now, as I said, this is not limited to military anymore and satellite communication. Ourselves in CAS, we are trying to deploy a testbed, and when we say testbed, we are just trying to, as I will mention later on, characterize the optical channel, because a lot of work has been done in different parts of the world, but not much in the Middle East. But basically, so we went ahead and tried to check if there are some companies that sell these products. And there are plenty of companies. These are 3 examples from Canada, US, and South Africa. And basically, with around $20,000, you can get a really good, basically, pair of transceivers with all kind of technology, which I will be talking about later on, hybrid RF-FSO, MIMO. You can have decent data rates, 2.5 gigabits here with a backup link of RF of 150 megabit per second. And again, I will explain that to you later on. Just to tell you that, again, this is not science fiction, let's say. It is reality. You can go on the web and make your order and buy your transceivers and connect to the network, and it's going to be up and running the next day you install it. So, just to further illustrate that, actually, it was just a couple of weeks ago, I think early March, a friend of mine forwarded to me this, video, short movie that I would like to share with you. It was in CNN.
High-frequency trading, financial interactions driven by computer algorithms that
so we'll restart again.
Moments drive.
Okay, so this was like basically a small kind of movie shown on CNN about 2 weeks ago, and showing, just as you will see, one application of free space optical communication. So I found it interesting, and I will tell you what I did with it after that. Beyond presenting it the first time to you here, I will tell you what I did with it. So tell me if you hear it well or not. Huh?
Financial interactions driven by computer algorithms that capitalize on tiny market movements drive big profits. Timing is everything in these transactions, and firms are in a constant race to beat each other on how fast the transaction happens. One company has devised a new way to make the trades even faster.
It's a laser that's infrared. It can go up to 15 kilometers, and it's the same one that's actually used in your remote control.
The laser takes about half the time as sending the same transaction through a traditional fiber optic cable. Based on the same technology fighter jets use to communicate, Innova partnered with another communication company, Optics, to create ground-based towers with lasers at the top. The lasers have a line of sight from one to another, enabling them to send data back and forth. Though there are limits, large distances are still an issue.
The maximum distance today is about 10 kilometers. Between the New York Stock Exchange and NASDAQ, that's about a 50-kilometer run. And so what that equates to then is 2 endpoints, 3 midpoints, for a total of 5 hops. You have to avoid blockages, trees, large topographical obstructions.
It's not just obstructions the lasers have to deal with. They also have heaters to keep snow and ice off the lens, the ability to stay aligned if the building sways on a windy day, and even visors to protect them from bird droppings. There's also a radio frequency antenna, commonly known as RF, that broadcasts the data at the same time as the laser.
Lasers don't like fog. That's okay, because then it runs on the RF side of things. RF doesn't like rain, but that's okay. The laser doesn't mind rain. So what that gives to the users is 99.9% availability, or equivalent to fiber through the air.
Despite the distance and need for many repeaters to keep the signal going, Innova is already developing a path between New York and Chicago with ambitious plans to connect other financial centers around the world.
We want to democratize access. We want to build this once, and then that's it. And then everyone participates in it.
Matt Stewart, CNN Money, New York.
Okay. So, I mean, the purpose of this short kind of documentary from CNN was just to, okay, let me go back here. Full screen mode, right? Okay, so yeah, this was an application obviously that I was not aware of more than 2 weeks ago, where basically laser or FSO was chosen, or was a good technology for high-speed traders, which means what they are saying here is that they are able to beat the fiber optics wireline network by using this FSO links, because the transaction can be done faster through an FSO links. And what surprised me more, a lot of actually interesting keywords have been used here. The hybrid RF FSO we shall be talking about, the multi-hop communication, many of the technologies that we are using for our research, and some people are saying, you know, you are not going to be able to get the reliability you want with these kind of links. They have been addressed here in a practical systems, and people are talking about a link between New York and Chicago. I don't know for those of you who visit the US, but this is not very close to each other. We are talking about hundreds of kilometers of FSO links. It was a surprise to me to hear that they are trying to adventure and getting into these kind of long range communication using only FSO. Obviously, this was not envisioned for FSO, I think, in the first place. But having seen that, so I'll tell you how I use that. So that's just a parenthesis. Now, as I told you, I'm a newcomer to this community. It's a small community of free space optical communication. Many people in, of course, the traditional optic engineering, which are different kind of background, but there are a few people who got into recently free space optical communication from our community, from communication theory. But my first surprise, so we start, I mean, I reviewed one paper, I got interested, I got students working on the topic, and then we start publishing in this area, and the first time we tried to submit a paper to IEEE transaction wireless communication. So as soon as I was submitted, like after a couple of days, the editor-in-chief rejected the paper. The reason is we don't accept optical wireless in transaction wireless communication. I was surprised, I didn't want to argue, but they say no, this is only for RF. We don't accept any visible light communication, any free space optical, any infrared communication in transaction wireless communication. So as I said, I didn't try to argue because it's wireless. I said it's wireless too, but I forgot about the issue, and I waited until we got a new editor-in-chief, and we have a new editor-in-chief, and I started the communication with him, telling him that basically I don't see why we should, as communication theorists, submit our work to IEEE transaction photonics. And actually, we got one paper there accepted, or IEEE transaction, or Journal of Light Wave Technology. A lot of the work goes either to GLT, which are very good journal, by the way. But I felt that we should submit our work to our traditional journals, such as IEEE transaction wireless communication. And and the new editor, he was, I think, listening. He was surprised himself why we should not consider this. And then, as part of discussion, this movie came, so I sent him this also. I told him, you know, look at this link. You know, people are talking about free space optical communication for very practical application, and still now in the discussion editorial board to see if they are going to reverse decision of accepting optical wireless communication articles in IEEE transactional wireless communication. Just to tell you, sometime, you know, journals get into this mode of exclusion, and while, I mean, there are plenty, I think, of good paper that can be accepted in this area, especially that they are using a lot of the techniques that essentially we are expert in, and that I think should end up in these kind of journals. So let us try to get a little bit more technical and talk about what are the issues I mean one has to face when basically he has or she has to design an optical free space optical link. The first thing that comes into mind when I would like to talk about free space optical communication is the type of detection that's being used. So there are two kinds of detection. There is the traditional so-called intensity modulation direct detection scheme, which is basically very simple, just capitalize on the intensity of light to send zeros and ones or symbols, like with ppm or basically on-off keying. Obviously, it's a very simple scheme. It does not require any adaptive control system in the sense you don't need to know the in-phase, quadrature, state of the phase or polarization of the wave. And traditionally, optical communication engineers have been using mostly this kind of detection and transmission scheme over FSO. Now, more recently, people are trying to get more greedy. As it is the case actually in the fiber optic communication, people are trying to get better performance, better SNR sensitivity, and are advocating for coherent modulation with heterodyne detection, trying to take advantage of the in-phase and quadrature. Obviously, this will lead to a better SNR, but this comes at the expense of a more sophisticated receiver that have to track the phase and the polarization. Now, mathematically speaking, and I'm not involved much into the receiver designs, but I'm interested mostly in the performance analysis. One of the key aspects that one has to notice, and initially I thought was a mistake in many of the papers, but actually that's something that comes out of the basically calculation of the SNR. The irradiance is like basically the power, the power of in the light. That's called irradiance. When you do an SNR calculation and when you look at a direct detection kind of scheme, the SNR will be proportional to the irradiance square. So gamma will be proportional to I square. Whereas when you are looking at heterodyne detection, gamma will be proportional to I. That's just a mathematical fact that is important because later on when you would like to do performance analysis, you have to basically be careful in terms of your SNR calculation or averaging over kind of distributions on what kind of detection has been used. Another key aspect that one has to look at is the notion of alignment or pointing error. Now, this is a table that was picked from one of the, actually I should put a reference here to one website that I picked this nice table from. Is essentially when we are talking about an extremely narrow beam, you better keep this beam aligned. So basically the communication is not cut. The problem is that there are some vibration or some basically swaying that can happen and that can basically make the beam move away from its initial basically position. So you have all kind of vibration. You have the small tip or tilt due to thermal expansion. These happen at a frequency of once per day. They are very slow processes, but the magnitude can be quite high. Then you have the wind that can lead to some sway of building phenomena, and that can be once every seconds. And then you have all kind of vibration that are in the building due to equipment door slamming, as an example here. So basically the magnitude may not be very big, but it can lead to very frequent pointing error or misalignment. So the pointing error problem is a crucial problem that has been looked at over many papers actually, and there has been models developed to basically capture this basically pointing error phenomena. And the model is quite simple, and I will tell you the starting model was done by Haranovic in McMaster University, or the Haranovic team in McMaster University. And what they assumed is, they assumed that initially the beam when was designed and when was installed was perfectly aligned, which means transmitter and receiver were exactly at the center looking at each other. And then because of the movement of either one of them, you have vibration in the horizontal direction and vibration in the vertical direction. And the natural way to model this vibration is to model them as Gaussian random variables. So you are having basically pointing error in the x dimension that are Gaussian and pointing error in the y dimension that are Gaussian. You look at the distribution of the amplitude of two Gaussian in a Cartesian domain, you end up with the Rayleigh distribution. And that was basically the starting point of a model that was integrated into an SNR calculation done by Haranovic. This model is characterized by the so-called Xi parameter, which can be viewed as a ratio between the equivalent beam radius and the pointing error jitter, or the error variance of these vibrations. So you can think of it as you have, this is the beam radius, or the beam diameter, if you will, and then within this beam you have this pointing error. So The Xi is the ratio of this beam over the jitter. If this ratio is big, going to infinity, essentially you don't have pointing error because essentially the error are still within the beam. But if Xi becomes smaller and smaller, which means the jitter or the variance of this pointing error are exceeding the beam radius, you are getting into serious pointing errors, and as such you will have essentially a serious degradation in your signal to noise ratio. Now, what are the possible solutions that one has to use to basically mitigate the effect of pointing error? When you deal with a short-range FSO link, one simple and easy solution, and this you can control, is basically you increase the beam divergence. Now, the fact that if you increase the beam divergence, what's going to happen, the spot at the receiver end is going to be larger. The larger the spot at the receiver end, the less you're going to be affected by the pointing error, because your receiver will be anywhere in the spot. Even if there are some variation in the spot, you'll be still capturing some of the optical power that's available out there. Now, on the other hand, if you are talking about a long-range FSO, you would like to maintain one of the main advantages of the FSO link, which is the narrow beam focused energy kind of link, and then you will put in place a sophisticated pointing, acquisition, and tracking system. This is the same technology that has been used, for example, for missile guiding through lasers or like robotic arm guiding. It's the same technology that has been used for this kind of pointing and tracking system that is being used for FSO. You can have either a fixed or like slow moving tracking system for short buildings, and you can even have a more fast or active tracking systems for tall buildings. So sophisticated FSO systems that are on the market now will have tracking system to make sure that at any given time you have perfect or nearly perfect alignment between transmitter and receiver, because indeed the effect on the performance can be quite serious if you have a misalignment between transmitter and receiver. Now, the other important basically factor that degrades the performance of an FSO link is atmosphere. An atmosphere will affect the FSO link in two ways. There are losses. When I say losses, these are long-term losses, loss that happens over a relatively long period of time. Okay? And there is turbulence or scintillation, which I will be talking about in the next slide. So what are the losses? The losses are due to mainly, basically, weather condition. Essentially, the general rule of thumb that I learned by looking at different papers in this area, the closer the size of your wavelength is to the basically particle that is involved in the weather, the higher is the losses that you are going to experience. So for instance, then this is called the Mie scattering. It is basically observed that raindrops and snow droplet are typically bigger than the FSO wavelength, which means the FSO wavelength, the nanometer I was talking about earlier, is basically much smaller than a raindrop or a snow. And as such, although rain and snow will affect FSO, the degradation due to rain and snow is not that important. Okay? People can live with a certain level of rain and snow. I mean, in a reasonable way, of course. However, what was observed is that the fog droplets are closer in size to the FSO wavelength. And as such, fog is the biggest, I would say, enemy of FSO link. And actually, maybe naturally, you can view it from a visibility perspective. If you have a thick fog, the light is not going to go through this thick fog, and as such, you cannot communicate reliably over a thick fog. Now, the mist is anywhere between fog and the mist, la brume, it's like less than fog, so people can live with a certain level of mist. And the way fog and mist are defined, fog is when the visibility is less than 1 kilometer, mist is when you have visibility 1 kilometer and above. So mist is, you have a better visibility than fog. Now the other big atmospheric loss component is the smog, which is essentially a combination of smoke and gases like air pollutant. And basically the problem with the smog is that it can contain particle mass of different sizes. You don't know, depending on the industry that is close to the area that are basically polluting the atmosphere, and depending on the kind of particle that are being emitted, you can have all kind of atmospheric loss to the FSO link. So if you look here at, and again, these have to be looked at with one should not believe absolutely these numbers, because you need to know many more, you need to know much more information about, for example, how much rain, like the rate of the rain, so on, to be able to get with these numbers. But typical regular rain kind of situation will give you an attenuation of about 9 dB per kilometer, snow 12 dB, mist, which is basically light kind of fog, 12 dB per kilometer. But when we talk about heavy fog, you can essentially lose your link. We are talking about 200 dB per kilometer, which is essentially complete shutdown of your communication link. So fog is the biggest enemy of an FSO communication system. Now, how do you mitigate atmospheric losses? So the first way is to basically use a mesh architecture. You should not use only point-to-point. You should have basically links going in all directions, and the mesh architecture can give you the opportunity to use different routes according to weather conditions, and the route diversity can help you basically perform in a satisfactory fashion in all conditions. Now, obviously, a very simple also mechanism that is being used in wireless communication is power control. And because it's a slow process, these are very slow process. When you have fog, you have it for, basically maybe 3-4 hours on the row. So that power control can be used basically to compensate for the extra loss that you will see through the channel or during rain condition or during snow condition. But actually, the most practical, and I would say, solution that is essentially deployed in most commercial system is so-called hybrid RF FSO. And the CNN documentary was talking about that. So the idea here, you see here your laser FSO, and you have here a 60 gigahertz kind of antenna, or millimeter wave antenna. And the idea that they work together as helping each other. So, and as he mentioned in the documentary, it's well mentioned in many papers that basically RF is more affected by rain, whereas FSO is less affected by rain, and the fog is the other way around. And usually the fact you don't have rain and fog simultaneously. So all these facts combine together to give you a robust hybrid RF FSO system that can give you high availability. But actually the way these RF FSO systems are usually deployed, they are deployed in a switch mode, which means priority is typically given to the FSO link. Why? Because FSO link is going to give you the high data rate that you would like to see always. And then if the FSO link basically lose its connectivity because of fog or rain or whatever, you switch to the RF link to pick up basically and to maintain at least a decent kind of communication. You see in the commercial example I gave earlier, typically you can you have a 2.5 gigabit per second when you are using FSO, and you will have to go to hundreds of megabit per second only when you are on RF, okay? So, but at least it maintains connectivity. Now, but actually, more recently, people actually, even information theory, and it's not complicated, but basically they are trying to play with the different kind of channel characteristics, are using more, are advocating more for a joint usage of these two communication links. At the end of the day, you have an RF link with a certain capacity, you have an FSO link with another capacity, and you can multiplex data over these two links when everything is perfect. You have clear sky condition. You can have the 2.5 gigabits per second coming from your FSO plus a few hundred megabits per second coming from the RF. And then if either one of them fails, you get at least one of them being up and running. So the better way of using this hybrid RF FSO system is actually to use them jointly and actually to encode data jointly. And there are people in coding area or like using sophisticated coding techniques to basically transmit simultaneously on these two channels. So, as I told you, atmosphere, when we talk about FSO, come with two problems. The losses, and we talked about the loss. When I say loss, they are not deterministic in the sense that they are random because of the fact they happen with fog, rain, and with snow, but they are slowly varying process. That we are talking about hours. That's the time scale at which this event happen. But the other important factor that affects an FSO link is scintillation, which is equivalent to fading in wireless. Those of you and those of us actually who have been working quite a bit in the wireless RF area, we are all familiar with the RF main problem, which is multipath fading. Scintillation, it's a very similar phenomena. So the way you observe scintillation in FSO link is basically at the receiver end, you will see intensity fluctuation that are going to be extremely fast, even under perfect slide condition and under perfect alignment between transmitter and receiver. And this is due to the variation in temperature among air pockets will lead to a variation in the air refraction index along the propagation path. Basically, and I'm not an expert in this field, but if you go in details and read about some of the paper written by optics and physics people, they relate the scintillation phenomena to the notion of atmospheric turbulence theory. So atmospheric, like the variation of temperature along the path of a wave can create turbulence, and this turbulence can create at the end scintillation, or if you will, signal fluctuation at the receiver end. Now, the way we characterize scintillation is so-called through the scintillation index, and the scintillation index, sigma I square, is nothing else but basically a normalized variance of the signal strength. So sigma I square is the variance of I is the irradiance. You can think of it as the power of the receiver signal at the FSO photodetector. So you have the variance of this I divided by the mean square, or normalized variance, and that's called the scintillation index. Now, this scintillation index depends on the Rite-of number, which comes from the, as I told you, from the atmospheric turbulence theory. So the Rite-of number, sigma r, depends on this Cn square. It's a refraction index number that is function of the temperature along the path. The k is 2 pi over lambda. L is the length of the path. And basically, what you notice here, you have basically maybe 3 regimes. We have what we call the weak fluctuation or the weak turbulence regime, where the scintillation index is roughly equal to sigma r, and that's called weak turbulence. Then you have a moderate turbulence regime, and then here we have what we call a strong turbulence regime. This is summarized here, and that's commonly used in the literature. As if you read some paper in FSO, I will give you even some number down the road. Basically, the weak turbulence regime is this regime, when the Rite-of number is very small compared to 1, and in this case, scintillation index is roughly equal to sigma r, okay, square. Now you have the moderate turbulence regime when the Rite-of number is around 1, and then if the Rite-of number, which again depends on the temperature along the path and the length of the path and so on, is very big compared to 1, you are dealing with a strong turbulence regime. Now this is the, I would say, physical characterization of the atmospheric scintillation. Now, from our perspective as communication engineer, what you would like to see, what is the distribution of the scintillation, because when you'll be looking at performance evaluation over of an FSO link over a fading or scintillating channel, you would like to know what is the distribution of I. So people have done some analysis, and I say propagation measurements and characterization of the statistical behavior of this channel, and they came up with these results. First of all, we are dealing with essentially a frequency flat fading channel. So that's easy. There is not much equalization to be done for the FSO outdoor channel. It's also time flat. It's not time selective. Basically, for the data rate, we are talking about the coherence time being 10 microsecond to 100 millisecond. It gives you more than enough to send multiple hundreds of symbols over the same fading state or scintillation state. And in terms of fading distribution that have been used to model this kind of scintillation phenomena, there is basically, for weak turbulence, you have the log normal kind of fading. For strong turbulence, the exponential distribution, which is like Rayleigh squared, okay? But if you want to have a general kind of model that fits in all kind of condition, there has been a strong kind of push to use the gamma-gamma, and I will talk a little bit what is the gamma-gamma model. You will see a lot of people talking about gamma-gamma, which is maybe those of you who are worked the RF area equivalent to the generalized K distribution. And again, I will define what it is in the next slide. Now, more generalized models have been developed more recently. Actually, one of my students presenting on Friday a paper on the so-called double gamma-gamma model, which gives you some additional degrees of freedom and allows to better fit the data, and you can still get some interesting closed-form solutions. Some Spanish group in Malaga developed a model they called Malaga model, you know, just based on, they are from Malaga, so they just called Malaga. And it's basically, these are generalization of the gamma-gamma distribution model. It gives you, again, additional degrees of freedom to better better feed the data. And of course, they will show you the more parameters you have, the better you can feed the data, and as such, the better you can come close to experimental results. So the gamma-gamma model, for those of you who are not familiar with it, is very simple. The good thing about it, it's very popular in the optical communication engineering area. Because it's valid for weak, moderate, and strong scintillation conditions. Basically, it goes with the principle that when you are talking about scintillation, you are dealing with fluctuation that happen at two scales, small scale and large scale. You can think of it like shadowing and fading in the RF area, but both are turbulence, but there is small scale turbulence and large scale turbulence. And then you model the first scale turbulence by a gamma distribution and the second one by a gamma distribution. So the very simple kind of summary of what is a gamma-gamma model, it is just the product of two gamma distributions. So if you take two random variables that are gamma distributed, and you know what's gamma, right? It's like a square of an Nakagami or like a gamma distribution, and you multiply them with each other, the distribution of the product is going to be called, in the optical communication community, a gamma-gamma model. This model, as I told you, has been used in the RF community when you would like to model shadowing as a gamma distribution and fading as a Nakagami distribution. You end up also with the product of two gamma, but it's called typically a generalized K distribution because it was observed as a generalization of the K distribution, which was a product of an exponential and a gamma, where exponential was used to model the Rayleigh fading, if you will, or the square of a Rayleigh fading, and gamma was used to model the shadowing. So it's exactly the same mathematical kind of dependence on I, but in the optical domain it will be called the gamma-gamma. And on the top of that, when you talk about gamma-gamma, actually, so what are the parameters that you see in a gamma-gamma model? So you have the I, which is the scintillation parameter, this is the fluctuating kind of intensity of light. Alpha and beta are physical parameters that are actually the parameter for the original gamma distribution that are going to be function of basically turbulence condition. So these are typically linked to Cn square and to basically the Rykov number. And there are some tables that you will see in some of the optical communication books that will tell you, for example, actually they're here, when you are dealing with weak channel condition, a weak turbulence condition, a good example of alpha and beta are given by this. And that's the resulting scintillation index. It's a small scintillation index. And notice always that alpha is always bigger than beta. That's also an observation that is a fact in the modeling of the channel, symmetrical actually, alpha and beta, and alpha is always picked as bigger than beta. And basically, these are typical parameters for a weak turbulence condition, typical parameters for moderate turbulence condition, and these are typical parameters for strong turbulence condition. So what do you notice here? Obviously, this will correspond to the weak turbulence condition. That's the best fading state. This will be the moderate fading condition, and the one that is closer, where the irradiance is the weakest possible, will be the strongest kind of turbulence condition. So these are examples of the PDF of a gamma-gamma for three kind of turbulence condition. Now, how do you mitigate basically atmospheric scintillation? As you will see, those of you who have been working in RF, a lot of techniques we have been using in RF, you can just borrow them and use them in exactly the same way to basically improve the FSO link reliability. Obviously, time diversity, but because of the high data rate of an FSO link, because of the long coherence time also of the FSO link, this will come at the expense of a very long delay. I gave you some numbers, like in the order of milliseconds of coherence time. So it's a long delay, and you'll need also to buffer data a lot if you are using high data rate, and large buffer size. Frequency diversity, you have multiple wavelengths. You can capitalize on that to transmit, instead of multiplexing data, to transmit redundantly information over multiple wavelengths. But you will face a lot of correlation, and a lot of paper looked at the performance of, like in RF, basically effect of correlation on the performance of diverse systems. And then you can, of course, use space diversity. It comes in two flavors. The first flavor of space diversity is to use what we call aperture averaging. So basically, instead of having multiple receivers, you just end up with a receiver with a large diameter, which is going to observe multiple realization of the same signals, and you use what we call aperture averaging. But this comes at the expense of a higher noise also level, which maybe can affect the SNR. But also you can use all kind of CMO, MISO, MIMO with multiple lasers or multiple beam and multiple aperture at the transmitter and receiver to combat fading. A lot of work by Murad Usal, for example, looking at space-time coding in the context of FSO link. I have done with my group some work on MIMO calibration or MIMO power allocation in FSO. There are sometimes some variation to the problem that make it a little bit unique. When, for example, you need to deal with intensity that is always positive, so you don't have like plus or minus 1 in your data stream. Only positive data has to be basically transmitted. Makes sometimes the problem different from an RF problem. But also, a lot of work has been done actually in the context of relay communication. As mentioned in the small video I showed you earlier, the range is limited, and as such you need to have multi-hop communication. And we start talking about multi-hop communication. Many of us in this room here looked at cooperative communication in the context of RF. The same kind of techniques, but with different channel model, with different kind of mathematical also formula for the SNR, can be used to basically look at problem of relay selection, multi-user diversity, and multi-hop communication in the context of FSO, or in the context of hybrid RF FSO. And I will give you some work, some example of the work done by the group, illustrating how some of the RF kind of work can be reused in a way, but of course with new challenges and with new mathematical complication in the context of FSO. So if you want to summarize, and we'll have a break after that, this slide is here to show you the main challenges that I have been talking about for the last, I don't know, half an hour or 45 minutes, and some of the solutions that have been proposed. So FSO is a very good technology. It has some niche applications. It's being, basically, it's being kind of examined for multiple kind of interesting new challenges. But of course, it has problems. The main problems are like any communication problem. There is a noise problem due to, the background radiation or like any communication system, the noise. So you need to develop more sensitive detectors, filters that kind of eliminate noise. You may want to go to, instead of the classical IMDD detection, you want to go to heterodyne detection to get a coherent kind of scheme that give you additional performance, provided that you are able to monitor the state of the channel properly. You have a strong free space path loss at this high optical wavelength. As such, you will have to deal with a limited range for this FSO link, but you can use multi-hop communication to compensate for this limited range. You have also all kind of losses due to atmosphere, rain, snow, fog, smog, etc. And you have all kind of solutions that I talked about: power control, mesh architecture, hybrid RF FSO, which we talked about also. And then you have the other problem that atmosphere brings to the picture is a so-called turbulence or scintillation, or if you will, fading, like in the RF world. And the way you can combat that is the way we mitigate that in the RF world by using all kind of diversity systems in space, in time, and in frequency, or cooperative diversity using relay. And then the extra problem that you see basically in FSO that obviously you don't see in standard RF, although in millimeter wave people start seeing pointing error problems, basically is a problem of pointing errors, and that we require tracking system to be able to align the system perfectly, or at least close to perfect. Okay, so let me stop at this point, have a small break, and then we can have questions also, and then we'll go into some of the research direction, at least done within my group. Yes, let's go with questions.
Okay, thank you very much for this nice talk, very interesting. Maybe I should say lightning talk.
Okay, thanks.
Actually, we learned a lot about this FSO technique, but my question is about VLC, because I ultimately saw, a couple of months ago, I saw a video about what we call Li-Fi.
Which is VLC.
Yeah, which is VLC.
Yeah.
But I didn't understand very well the technique, because they talked about, like you said, vibration of the light in the room, but I really, actually, I didn't understand very well. Maybe you have more idea.
I have done a little bit of work.
Thank you.
Most of my work has been on the FSO. We wrote only 1 or 2 papers on the VLC. But VLC, from my understanding, and Li-Fi, so Li-Fi, Wi-Fi, we know what it is. Li-Fi is laser fidelity. So it's called Li-Fi. It has been used by, I don't know if you know him, I forgot his name now, Haas. Yeah, Haas in Edinburgh, University of Edinburgh. So he came up with this consortium, and he called his consortium Li-Fi. And there is a few other people, like there are a lot of good people in Northumbria University, Newcastle, who also work on VLC. There are people also in, like Murad Usal, he used to be in Waterloo, now he's in Istanbul, so works on VLC. But what it is basically the light as it is now. Instead of being like just you know, like used for lighting only, you can modulate extremely fast the light and use that modulation. You have a very sensitive photodetector that will be able to detect this variation in light intensity that your eye will not be able to detect, or will not affect your eye. Or you will use the right LED that's not going to change the wavelength based on this variation of the light intensity, and use that kind of modulation of light to send information. As simple as that. So that's my understanding. That's how we are having using it as a model, and that's what people are talking about for airport, train stations, airplanes. Basically, it's more for downlink. Obviously, it's not for uplink. Like basically, you have your laptop. Like assume each one of you have your laptop. Light is available, and the information is going to come and in a downlink fashion. Yes.
Maybe this is very interesting, and maybe it is annoying a little bit the operators, because they won't have any longer any. I mean, any base station or access point?
I attended a talk where they have been discussed. I mean, a lot of players are getting into this. First of all, the main players actually is, first of all, the people who build the bulbs. Philips, for example. Philips is very interested in this technology because they build bulbs, LED bulbs, and they can use that to basically market their bulbs not only for lighting but also for communication. Now the operators, yes, I mean, it's part of their market, but the operator, I mean, they will give you at the end of the day, they will bring you basically connection to the home. This is more for indoor. Huh? So basically, you are switching the Wi-Fi connection by Li-Fi, but it's only for downlink. The uplink have to still be done through an RF link. No, because you have to, you know, unless you have to align perfectly your laptop to the photodetector somewhere in the roof to be able to send your information. But it is more one-way kind of communication. But I think it's very interesting, as I tell you, Japanese and Korean, and this is what is missing now in my talk is references. And I promised Leila to add a set of references at the end. And there are a lot of good books, and actually that go into details of VLC, FSO, even infrared communication.
Thank you very much.
Okay. Yes.
So typically, what is the order of magnitude of the energy per bit to have the 10 giga or something like that?
I'm not.
It should be strong.
Yeah. The only thing I can tell you is there has been some motivation to look at a low SNR capacity in the context of FSO, because the bandwidth is big. And like the bandwidth, you know, ultra-wideband communication is well known to be basically to go to the low SNR regime, basically. So, but what is the exact numbers? I don't know. I mean, how much the cost of per bit, like the energy efficiency of this communication in terms of absolute
Is it
number.
better than regular?
I think, I mean, people are saying it's more energy efficient. So I assume because the energy is more focused into one direction, but you can end up with very low SNRs because if the range is more, or like the fading is very strong, so you may end up, and the bandwidth is big, you may end up with a low SNR regime. But in terms of energy efficiency, definitely it is well known as being an energy efficient solution. But in terms of how energy efficient it is compared to RF, I don't have numbers in mind.
Okay.
Thank you for this talk. I would like to ask about even in FSO we are using point-to-point transmission, but I think one challenge is how to enable all optical switching using FSO. So switching, I think it's
switching from where to where?
Switching from one light to another light without optical electrical conversion.
I mean, like
for example, using WDM or OPS, optical packet switching, or optical burst switching technology, for example. in free space transmission?
Yeah, the practical implementation, again, I'm not a optical engineering specialist, but what I can tell you is definitely there are some prototype that have been published, and the results I gave you are prototype of FSO link that have been tested over the air, actually underwater also, and many of these are using WDM to be able to achieve this high capacity. So I think the best way to answer your question is to give you a reference to some of these papers that appear more in IEEE photonics, or they are more in the photonics area in terms of device and prototypes. That you may get an answer to your question in these kind of journals. But please remind me, and I will give you the link to these. It's the good people in this area are, as I told you, Japanese at the University of near Tokyo. It's not Tokyo University; it's another university. But in Pisa, they're the best. Basically, or the recent results or records have been published by people at Anna University in Pisa, and they are more from physics department. Yeah, one second. Yes.
Thank you. You mentioned many challenges for free space optical communication, like atmospheric losses and atmospheric turbulence. But what about the installation of birds on this equipment? So
birds.
Yes, like.
I mean, yeah, of course, you may have all these kind of, yeah, I assume you can have all kind of, also the mirror, or I mean, it has to be clean, of course. The laser lens has to be clean. If there are birds, people talk about that. If there are birds in the way or trees, these are obstructions that can affect basically the communication link or degrade the SNR. So you assume that they are part of the randomness of the that you can face when you communicate over these kind of links. But yes, I mean, you are talking about like birds that come across the path, right? On the top of the laser, you mean? Huh?
Yes, for our town, we see it always, this type of...
Yeah, I mean, obviously they have been maintained and cleaned, huh? Yeah, probably. I mean, probably there are some problems that have to be like maintenance and cleaning. You have to maintain them clean and maintain and up and running. Yeah.
Yeah, merci. Yeah, I mean, it seems very interesting for lots of applications. The most promising, it seems, is the last mile kind of applications.
But temporary events also.
Yeah, and satellite communication for sure. What about, I mean, is there any possibility or tendency to explore things in a mobile environment?
I will talk later on some of the work we have done with one of my students on how maybe this can be explored in a mobile environment. Because although, from military perspective, I mean, it was a little bit strange, although maybe most of the work is classified. They use that for airplane-to-airplane communication. You cannot be more mobile than two airplanes. Yes. But they are able to track, like basically the movement of these two airplanes and keep the laser and photodetector aligned. So basically it can handle mobility. But obviously this is for military application with very sophisticated equipment. That's probably not for mass deployment for mobile users. But we have a solution that I will be talking about in some of the highlights of the work down the road. But also, I think, as I mentioned earlier, it can be a very good solution for the wireless backhaul. I'm not the only one saying that. People, I mean, I don't know how many of you went to ICC. They are talking about millimeter wave as a great solution for the backhaul. I think millimeter wave combined with FSO, creating a hybrid RF FSO system, can be a great solution for the backhaul, because you can get extra capacity, and together they can give you the reliability you need for the backhaul, where you need the 10-9, 10-8 kind of requirement for the backhaul. Yes. So I think that maybe it can be an interesting application for wireless in the backhaul area. But for mobility, yes, because the user will be very mobile. I don't think you'll be installing on the top of every user a tracking system to keep track of what he's doing and where he's moving.
Great, yeah, so you talked about Li-Fi and the fact that, and then you also mentioned that there should be alignment, and that's why you only have like a downlink. But I mean, so the alignment between the light and the laptop, for example? When you say
I mean, basically, yes. I mean, the photodetector will be in the laptop.
Yeah.
So, and the light will be coming, light can have certain spot that can be more than one laptop, like one area. And you can think even, and I can show you some paper, a cellular topology in a room like this, where every light will have a certain coverage area. You can have overlap, you can have interference. Everything that can be done at the cellular can be done in the room level. Okay. But now, for the uplink, for you to transmit back, you need to have a laser or like some kind of LED, and then you have to have a photodetector, but you have a lot of, it's not practical to have a strong LED in your laptop. So it's more practical to have just a photodetector, and people are arguing for the fact that mostly you'll be downlinking, you need rate for the downlink to download movies and so on. For the uplink, maybe the link is less bottleneck.
But I mean, just to a follow-up question, does that mean that equalization is not an issue? Because you mentioned...
No, equalization for VLC, okay. Why actually I didn't do much work on VLC? Yeah. Because VLC, there is not much fading to be done. I mean, most of the work in VLC, they tell you there is not much fading. It's line of sight, it's very stable channel. It's more actually multipath in terms of ISI, and most of the work in VLC is equalization. A lot of good work in equalization. But there is not much work on fading or diversity. If there is MIMO, it's for multiplexing data. It's not for diversity purpose. There is not much fading in VLC. And that's why I didn't do much work, because I like problems where there is fading. But there is a lot of work actually in equalization. And if you're interested, I can give you something.
No, but I mean, sorry, but I mean, the thing is, if it's mostly like point to point or like direct.
For VLC actually it can be more omnidirectional. It can be because LED laser tends to be more point to point. LED tend to be more omnidirectional, like light. So, and you can have also diffuse kind of transmission, reflections, and multipath and so on. Okay. Yes. As I said, FSO can complement the fiber optic wireline network, either as being the last mile solution. Basically, you reach a place through a fiber optic, and that's the only place in a particular area that has fiber optic connectivity, and the other place will be connecting to the fiber optic connection through an FSO link with that building. Or it can be, as like mentioned in one of the slides, as a backup, if somehow the wireline network is shut down or is an outage. And the FSO can pick up and can act as the main network.
Okay.
Yeah.
I have a question about atmosphere
scintillation.
Yeah. The question is, it depends on the environment. For example, in Tunisia, we have humidity. I don't know how to say in English or in French, ajej in our ajej in Tunisian ajej. So we have a lot of particles, silicium and so on. So how it will affect the channel?
No, actually, that's the main. I mean, really. So now there is, as I told you, it's a community. If you go to this, there are some small workshops on optical communication, and there are different communities that come to this workshop. Like a subset of these people are propagation people who do propagation measurements. And a lot of papers have been published in Germany, somehow Czech Republic, I don't know why, but they have a lot of work on this, and the Scandinavian countries, trying to characterize the FSO channel. Okay, the VLC is indoor. Usually there is no much. I mean, there is experimental work, but it's more like about multipath and the equalization. But for the FSO, weather is critical. The effect of snow, or rain, mist, fog, all kind of paper you can see on this topic. Now, there is not much work that has been done on basically, for example, sandstorm. Saudi Arabia, you would like to see the effect of sandstorm, which is like ajej. So basically, that's what you would like to see. So actually, that's what I was saying. We got a proposal from CACTS. I don't know if you know him, Habib Fathallah. Anyone knows Habib? Yeah, so he's in case, I don't know if you know him, he's in King Saud University. So obviously I'm not an experimentalist, I don't have a photonic lab or anything of this kind. But Habib has a very good lab in KSU, in Riyadh, King Saud University. So we wrote together a proposal for CACTS, and we are building 2 test beds, one in King Saud and one hopefully in KAUST. And the idea is to make very simple channel measurements, to try to, and like basically the test bed we proposed is to have just a pair of transmitter and receiver, and Habib is very good at, he has built that a lot in his lab, but we'll put it somewhere in Riyadh and somewhere in our campus with a set of sensors trying to capture wind, temperature, humidity, sand, like basically the density of sand, and try to correlate that to the strength of the signal. So this is a proposal that was approved, but you know, it takes time usually to get the money released. But that's a different story. But this is one of our objectives. Actually, you'll see one of my last slides is there are two projects we are trying to be involved in, where are relevant to, I think, to our part of the world. Is one to try to characterize the channel in Middle East, like in Saudi Arabia, and also another niche applications, underwater communication. There is a big interest now, and I went only a couple of times to this very small workshop on optical communication, where people are starting looking at optical communication as a solution to basically increase the data rate that have been stagnant for a long time underwater because people have been using only acoustical communication. So optical communication underwater, there are some few groups in the world that are looking at that, and we are trying also to start looking at this problem. And it's quite interesting, and you can achieve much higher data rate, but again, you have some challenge that you have to overcome.
Thank you.
Thank you. So I think we are ready for a small break, and then we'll pick it up from there.
Okay, thank you.
Thank you.